Okay, we're going to talk a little bit about some of the Esri hydrology tools, and most of the examples I'm going to show you in here, I believe, are taken from ArcGIS Desktop, ArcMap, Arc Toolbox, if you will. So some of this stuff will be a little different in Pro, but it'll be basically the same thing. So there's my obligatory early in the lecture yawn, so got that out of the way. So you work through these, see what these are, and then I'm going to give you another little video of a lab assignment. This is lab 7. It's not this week's lab, it's next week's lab, but I'm going to give it to you a little bit early about this rather than next week. So that'll give you a little more time to do it. So when we look at hydrology, Hydrology Toolbox has a plethora of tools, and we're going to look at what some of these include and what they do. For example, the basin tool, it makes raster delineating. It makes rasters delineate all drainage basins, but in order to do that, you have to have a flow direction raster. Then there's the fill tool. The fill tool fills sinks in a surface raster to remove what you might consider as small imperfections or spots that don't drain on a surface. We looked at some of the fill sinks tools last week in Saga. This is a more basic sort of tool here with Esri, designed just one size fits all. To run this tool, obviously you got to have a surface raster. Next, we're going to look at flow distance. We'll talk a little more about flow direction and flow accumulation later, but we'll work with flow distance first. It competes for each cell the horizontal or vertical components of minimum downslope distance. It follows the flow path to the cells and to the stream that they flow. It's an optional tool that it can do some other things there, but ultimately it requires a surface and a stream raster. Flow length calculates the upstream and downstream distance. It could be a weighted distance or the distance along a flow path. Again, requires flow direction. The sink tool, this creates a raster that identifies all the sinks or areas of internal drainage. Sinks are the things that you fill. The snap pour point tool, for example, it snaps pour points to the cell of the highest flow accumulation within a distance of where you click. The input raster or feature pour point data is required, and some sort of a flow accumulation raster is required. Quit yawning, Mike. The stream length tool is the one that assigns unique values to sections of a raster linear network between intersections. This basically requires stream and flow direction raster in order to work. Stream order assigns a numeric order to a segment of a raster. This represents branches on a linear network. It requires stream input and a flow direction. Streams to features converts a raster representing a linear network to features representing a linear network. It requires a stream raster and an input flow direction raster. And then watersheds basically determine the contributing area above a set of cells in a raster. In other words, you pick an area, 1, 2, multiple cells, and it looks at everything that drains to that point. It requires flow direction and an input raster or feature pour point data. So that's just a handful of the tools. Most of these are things that are built upon from flow direction, flow accumulation sort of things, and we'll talk a lot more about that in the upcoming slides. The pinnacle, if you will, of a lot of this hydrology stuff, in my mind, is something called a Topographic Wetness Index, a TWI. It has other names. It is sometimes called a compound topographic index. But what it is a steady state wetness index. And it involves a couple of different things. The upslope contributing area, so that's pick a location and it finds all the area that drains to that point. And a slope raster, so that it knows the relative change in elevation, and a couple of geometric functions. The value for each cell in the output raster is an index value, and that index value relates to local wetness. And so what it's telling you is, relative to the surrounding cells, how wet is this cell. And so, as is always the case with index values, the numerical meaning has no context except within its own scale. And so a value of 10 is wetter than 9, but it's not as wet as 11. Higher CTI values represent drainage depressions or locations with a lot of accumulation, while lower values represent crests and ridges or locations that have very steep slopes. When you're calculating these things, there's a couple of things you have to consider. Flow accumulation and slope are the big ones. How you calculate these things will affect the values. So when you calculate your catchment area or your flow accumulation, there's a couple of different techniques. There's at least 3 really common ways. One's called the D8, one is the D infinity, and one is the multiple flow directions, or the MFD. And slope calculations can also take different forms. In other words, it can be local slope from a pixel, max or minimum slope generated using a small neighborhood around each pixel. So maybe it's a 3 by 3, maybe it's a 9 by 9. You get the idea. And so these things actually impact a lot of this stuff. Here's a nice schematic. You guys, I believe, looked this up a couple weeks ago. We talk about the morphology and the types of things that we look at to compile topographic indices. Some areas concentrate and accelerate, some areas concentrate and decelerate, some disperse and accelerate, some disperse and accelerate. And if you look at this landscape, this complex landform, you see things that are convex or concave in up and down and across directions. And think of how that impacts the movement of water. Also realize that it could also be linear or planar in those directions, so that there's not just a handful of combinations, there's many more combinations of whether it's linear, convex, or concave. And so you could have 6 different or more combinations of those configurations. Upslope contributing area is sort of the first basic tenet of this process, and it works so that everything drains to a given point. And you extend this concept out to the entire raster surface so that everything goes somewhere and nothing stops in the raster. Everything has to leave the raster. It has to drain away. If it does that, then the cell that has the highest value in the upslope contributing area is the cell that has the largest area in the DEM. It's also likely one of the lowest cells in the DEM. Now, it can get a little squirrely because you can have some odd things along the edges of a DEM if they're not clipped, for example, to a watershed, if they're just arbitrarily selected. Before you can calculate flow accumulation, you have to understand the concept of flow direction. And so this idea that everything has to go somewhere is technically incorrect because we have things like sinkholes. But in order to do complex interconnective hydrologic functions, we need it to behave like it has to go somewhere. And so you have to determine the direction of flow, and that's the first problem we have. And once you have a direction, then you can literally just count up accumulation. So over here to the right, we've got this nice little grid, and these are elevation numbers, and you can see that bright red 94 is lower than everything around it. That is a sink. if we're going to look at a D8 or an MFD or a D infinity, with a D8, every cell flows into one of the surrounding 8 cells. It simply has to decide which one is the lowest, and that's where it goes. In multiple flow direction, every cell drains into every surrounding cell that is lower than it. So if 7 of those 8 surrounding cells are lower than the one in the middle, it drains divided up evenly between all 7. The D infinity is sort of a compromise between the D8 and the multiple flow direction. It divides up the flow between 1 or 2 cells. And it does this based on slope, and it does some calculations to figure out the direction of travel. And then it divides that up between those 2 cells, or just to 1, and it has some really complicated math to figure that out. And so that it does give you a more realistic expression of how overland flow would behave. But before you can do any of that, you have to take care of sinks. So we need it to be hydrologically continuous, so everything has to drain everywhere, everything has to drain somewhere. So 94 doesn't drain anywhere, so that's got to be fixed. A tool like fill sinks would identify low spots and then raise that elevation until it is higher than one of the surrounding cells. No more complicated than that. In this case, it has to reach a value of 101. At that point in time, it is no longer lower than all of its surrounding cells. It will now drain to somewhere. So let's look at how this process works. If we use the D8 method, it identifies low spots and raises them until everything goes somewhere, and then it has a single direction equation. There's no dispersion of flow. This really makes things get screwy in flatter locations. But essentially it starts in a circular fashion, and it finds the lowest surrounding cell, and that's the one it goes to. If multiple cells are equally lower, it goes to the first one it finds. And so that's not natural either. If we use the multiple flow direction, it divides the flow up across all of its neighboring cells that have lower elevations. So if this cell value here was 100, if all those surrounding cells to the bottom where the red arrows are going were lower than 100, that cell from 100 would be divided up between those other cells. If that was the apex or the top cell in the data set, then each of those 4 cells would get 1/4 of that cell. If that cell number 100 had those 4 above it draining into it, plus itself, that would be a total of 5 cells worth of area, and so each of those red 4 would get 1.25 cells. And that is how the flow accumulation would work. Whereas with direction, it's simply just figuring out the path. This is that complicated math. The D8 method looks at 8 triangular facets. So you take those cell centers from all 9 cells in a 3x3 grid. From the center to the outside one, this little box that they draw up gives you these various triangular facets. Knowing the elevation of the one in the middle and the outside, you can calculate the slope of the triangular plane. And whichever triangular plane has the steepest slope, that's the first sort of step in the process. Once you figure out that, it looks at the across plane slope. And it has some rules for how it works, but long story short, what happens is, if it is sufficiently steep enough from side to side, it will steer all the flow into one of those 2 endpoints at the base of the triangle. If it's not sufficiently steep enough compared to the slope in the direction of the big arrow, so if the big arrow is really steep and the side to sides isn't very steep, then it's going to divide that flow up between those 2 cells based on those equations. And that's how it does this. And so in some instances it all goes to one cell, in some instances it's divided evenly between two cells, and in most instances it's divided proportionally across the two relative to their individual changes in elevation. So here's what that kind of looks like from a D8 standpoint. You get something that looks a lot like this. If we look at the multiple flow directions, it looks more like this. And if we look at the D infinity, it looks more like this. Now you're probably asking, what the hell does all this mean? That just looks like checkerboards. Darker means more flow accumulation. Going from light to dark is just about the direction. If we look across a complex watershed, this is what a D8 method looks like. It becomes very linear because you pick one of 8 directions. And so you get something that looks very much like this, which in the early times, in the early stages of GIS years and years ago, this was a remarkably bold thing to be able to do. As processing efficiency increased, people didn't like aspects of the way the other D8 method calculated. They eventually came around to using this MFD, multiple flow direction system, where you get something that looks more like this, where everything is evenly divided up between all of its downslope neighbors. Again, not how it works in reality. But a much smoother output, a much more realistic looking output. And then there's sort of the compromise technique, the D infinity, which divides the flow up between one or two directions, not all the directions. Sometimes one, sometimes two, sometimes even, sometimes proportional. This turns out to be a more, I think, realistic expression of what overland flow seems to be. So let's take a look at how some of these things can appear. Here we have the D8, and we add to that the multiple flow direction, and we add to that D infinity, and you can see how we go from very coarse and linear to very smooth and vague to a compromised solution that has some of the better concepts of both of these techniques, and it ends up, I think, being a lot better way of doing it. Topographic Wetness Index is, as I mentioned earlier, a really interesting tool. This tool we use to calculate relative wetness, at least in terms of what we assume it to be. The raster values are relative, and so they only hold true within the specific study area. So a value of 10 in one watershed is not the same as 10 as in another. They're only within the analysis that you do. The values cannot be compared. If you alter the data set, you got to redo the analysis, etc. The formula for calculating it is simply this. At a given point, I, the index value, is equal to the natural log of A divided by the tangent B, where I is the index value, A is the upslope contributing area, and B is the topographic gradient, also known as slope. The tangent function is to convert back and forth between percent and degrees and slope. I can't remember offhand which one it is it uses, but if you have slope in the wrong format, you can simply drop the tangent part of the equation, and it's just upslope contributing area divided by slope. But at the end of the day, what does that mean? It means that wetness at a spot is related to how much area drains to there and how steep the terrain is. The more area that drains, the greater the amount of water potential. And then the steeper the area is, the more rapidly that water leaves, and hence making it drier. So if slope increases, then the denominator increases, thus making the value lower. If upslope contributing area increases, it makes the numerator larger, thus making the value greater. And that's basically how it works. Slope is an important role in a lot of hydraulic processes, and it is a determining factor for the movement of water all over the planet. If you have a lot of slope and steep terrains, water tends to concentrate, moves through channels, cuts across landscapes. In flatter areas, it slows down and it spreads out. All this has to do with how it ponds. It has to do with how materials that are carried in the water column settle out. You can see real expressions of the impact of slope just by looking at rivers and how you'll come down long stretches of narrow valleys where water flows rapidly, opening up into a larger bottom area. And then when it does that, it flattens out. The rate of slope decreases, the water speed slows down, it goes out over the banks, and as it does, the different particles begin to settle out. Larger ones closer to the edge of the river, smaller ones a little further, finer ones stay in the water and move downstream. All this driven by slope. All this driven by elevation. All this driven by the physical configuration of the surface of the earth. Stream power index is another useful tool. It is similar to the topographic wetness index, but instead of dividing by slope, we multiply by slope. What this tells us is that the relative erosive power or strength of a stream is equal to two factors: the area that contributes water to it, upslope contributing area, and the relative steepness of that stream. And so as slope increases, the power of the erosive force, the strength, if you will, of the stream increases. If the upslope contributing area gets larger, the volume of water, the erosive force, the power of the stream increases. So instead of dividing by, we simply multiply. The lab is going to be a little different from what it says on this slide. I thought I'd already changed this, but I guess I didn't. I'm going to give you a DEM I'm going to load up. It's of the entire state of West Virginia. I'm going to give you a lab video with some directions that I narrated last year or the year before. There'll be parts of what I say that doesn't line up with what's typed on the slides. Go with what's typed on the slides. You don't have to do West Virginia or Jefferson County. I'm going to give you a statewide 30-meter DEM. You can cut out a small area, something that's no more than maybe like the fourth the size of a county. If you're wondering what that means, look at the shape of West Virginia. There's 55 counties, so if you can imagine what 1/50th of the state's total area is, that's like average county size. And so I would tell you to pick an area that's smaller than that, and you should be able to do this without too much difficulty. You want to pick a big enough area that you have some character to look at, but you don't need to pick a whole county. If you look at the panhandles of the state out on the eastern panhandle, next to the Harpers Ferry area, there's 3 counties that make up that sort of lob out there at the end. If you want to pick, just a part of that very tip end, or just part of that upper section there near Harpers Ferry, that's fine. If you want to just draw a tiny box out in the middle of the state somewhere, that's fine too.